It's 3 o'clock, so we'll get started now. Welcome back to our fourth week. This week and next week will serve as an introduction to a field of math that's not really explored in school normally, called number theory, and it involves dealing mainly with integers. And today we'll be talking specifically about some of the fundamentals, including divisibility, factors, and bases. And as in previous weeks, the handout is already posted on the website, so feel free to pull it up and use it to help you follow along. We'll also follow the same structure as usual, starting with an introduction to each topic with sample problems, and then moving on towards more challenging competition questions towards the end. So we'll begin this week by going over some of the most common divisibility rules, but before that we need to define what divisibility means. An integer a can be said to divide another integer b if there exists another third integer k such that a times k equals b. So for example, the 2 divides 4 because there exists another integer, 2 times 2, which equals 4. This definition is pretty simple, but it gets useful when there's some weird exception cases like 0, which we'll see later. And for divisibility rules, many of you guys have seen these rules before, and while simplistic, they're still often used in middle school competitions such as math counts, and even on occasion the AMC 10. We'll provide some example problems from each of those contests over this lecture and subsequent homework. And we won't delve too far into the proofs for each of these this week. That's a topic more relevant for next week when we'll go further into number theory. So to start off, we have the divisibility rule for 2, and it's almost a common sense one. The last digit simply has to be even. So the last digit is 0, 2, 4, 6, or 8. It's divisible by 2. So next would be 3. 3 is also a pretty common one. It means that the sum of the digits is divisible by 3. So for example, if we took a number like 138, the digits sum to 1 plus 3 plus 8, which equals 12. And as 12 is clearly divisible by 3, 138 is also divisible by 3. So next would be 5, which again, like 2, has a very simple divisibility rule. Simply, the last digit has to be either a 0 or a 5. Next is 7. 7 is probably the most complicated divisibility rule you'll have to use for a contest, and even so, it shows up very rarely. It involves taking the last digit of the number, doubling it, and then subtracting it from the rest of the number. And then you can repeat this until the number is small enough such that you can see it's easily divisible by 7. So for example, if we took a number like 1512, we take the last digit, which is 2, double it to get 4, and then subtract it from 151. 151 minus 4 equals 147. And from this point, we could take the last digit again, 7, double it, and subtract from 14, which would give us 0. And as we mentioned in the beginning, 0 can be divided by 0 is divisible by every number, as 0 is an integer, so any number times 0 equals 0. So as 0 is divisible by 7, that means 1512 is also divisible by 7. The next one would be 9, which is basically the same rule as 3. The sum of the digits has to be divisible by 9. So we take some arbitrary random number, like let's say 213, 1236. Actually, dividing this would take a bit too much time, so we can simply add up the digits to get 3, 6, 7, 9, and then another 9 to get 18. And 18 is clearly divisible by 9, so this number is also divisible by 9. And the last major divisibility rule that you'll have to use in competition math is 11, which is actually somewhat frequently used. It involves taking the sum of all the odd place digits minus the sum of all the even place digits. And if that's divisible by 11, the overall number is divisible by 11. So for example, if we look at the number 11539, the odd place digits would be 1, 5, and 9, which sum up to 15, while the even place digits would be 1 and 3, which sum up to 4. Subtracting them gives us 11, which is quite obviously divisible by 11. So this larger number is also divisible by 11. So now we can note that we actually skipped over some. And while divisibility rules don't work neatly for every number, there are a couple more for which it's nice. For example, the powers of 2, such as 4 or 8, work such that for a number to be a multiple of 2 to the k, the last k digits must also be a multiple of 2 to the k. So for 4, that would mean the last 2 digits would have to be divisible by 4. So we took the number 912. We can immediately see that it's divisible by 4 as the last 2 digits are divisible by 4. Similarly, if we took 8, which is 2 cubed, we simply have to look at the last 3 digits. So if it was like 12008, this obviously, the last 3 digits are divisible by 8, so this overall number would also be divisible by 8. And there's one final special case where you can use divisibility rules, and it occurs when you have products of small primes. So for example, if we look at, let's say, 6, we can derive its divisibility rule by looking at its factors. Any number that's divisible by 6 will also be divisible by 2 and 3, and vice versa, as 2 and 3 share no common factors. Therefore, we just need to check that both the rules for 2 and 3 hold, which would mean that the digits sum to a multiple of 3, and the last digit is even. So in the same way, we could do this for any pairing of these rules that we've already have before us. So for example, 3 times 5 for 15, the last digit has to be 0 or 5, and the digits have to sum to 3. Or even something like 45. The last digit would have to be 0 or 5, and the digits would sum to 9. So even though we can combine all of them, just note that some of the pairings can result in rather complicated rules. So it's not always useful. And again, most extremely large numbers don't have convenient rules, and they're not particularly needed. So just knowing these 7 or 8 main rules and how to pair or triple them in special circumstances is the extent of divisibility needed for middle school competition. So now we'll move on to our next topic of factors.
All right, so one of the largest focuses on number theory are factors of a number. So a factor is basically any number or any positive integer that divides a number. So if we list out the factors of 6, the positive integers that divide 6 would be 1, since 6 divided by 1 is 6, 2, since 6 divided by 2 is 3, and then obviously 3, and then 6. So another special focus about factors are prime factors, because each number can be uniquely expressed as a product of its prime factors, called the prime factorization. So for example, 98 can be factored as 2 times 7 times 7, which we would write as 2 times 7 squared. Or let's say 24 can be written as 2 cubed times 3. So if you need a refresher on primes, you can check out handout 1, which is on our website, sometime after or during this lecture. So we'll look at 2 main consequences of factors today. The number of factors for a given number and the sum of the factors, since these are 2 topics that come up fairly often in competition math. So first, we'll look at the prime factorization of in the form of prime P1, where P is a prime, to the A1 power, and then P2 to the A2 power, etc. So we could find the number of factors of any number in the form of like P1 to the A1 times P2 to the A2 ... by considering how many possibilities there are to group together its prime factors. So obviously, if a number, let's say k, divides our original number, then obviously it has to be a divisor of n. So that means it can't have a power of, let's say, p1 greater than a1, because otherwise it would obviously not be able to divide n, since you would have one more 2 in it. So for example, a cannot possibly divide any like odd multiples of 4, so like 12 or 20, since there is only any odd power multiple of 4 can only be divided by 2 twice, whereas 8 is 2 to the 3rd power. So that means each factor of n can either be 0, 1, 2, 3, 8, 1, p to that power. So that means for the number of ways we can write it in terms of p1, they're exactly a1 plus 1 ways. And if we do this for each prime, we get that it is, for every prime, we take the power of that prime and then add 1 and multiply it to our previous product. So for example, let's say our number 12. We can write 12 as 2 squared times 3. So when we write it as 2 squared times 3, we obviously have the 2 primes 2 and 3. And the powers respectively are 2, which we will call A1 in this case, and then 3 to the 1, which will be A2. So then the factors of 12 can either be multiples of 2, 4, or 1, where they don't have any multiples of 2. So that means it can be 2 plus 1 possibilities with regards to powers of 2. And then the same with powers of 3, so we do 1 plus 1, and this gives us the number of factors of 12. So in this case, it will be 3 times 2, which is 6. And since 12 is pretty small, we can check this by hand. So the factors of 12, well, we can do them. So 1 obviously divides 12. 2, since 12 is even. 3, well, 12 is 3 times 4. And like we just said, since 12 is 3 times 4, 4 obviously divides it. Then 6 divides it, obviously, since 12 divided by 6 is 2. And then finally, 12 is a divisor of itself. And we can see here, there are exactly two instances of each power of 2. So 1 and 3 have exactly 0 powers of 2. 2 and 6 have 1 power of 2. And then 4 and 12 have exactly 2 powers of 2. And we can do the same with powers of 3. So this is where we get our formula. And this is very useful for counting the number of factors. So you don't really need to know how this formula comes about, but it's very important that you memorize like how to use this and like especially what to do, because counting the number of factors comes up very often. So next we'll go over the product of various factors. So similarly, we use a similar way of counting. So if we take the sum of each factor, right? Well, if you look back to our factors of 12, right? Exactly 2 of them are 2 to the 0, right? And exactly 2 of them are 2 to the 1, exactly 2 of them are 2 to the 2, right? And they come in pairs of, well, multiples of 3. So 2 to the 0 times 3 to the 0 is obviously 1. Then 2 to the 0 times 3 to the 1 is obviously 3, and so on. So since each factor can be expressed by some combination of these primes, we can actually factor this in a way that makes it much nicer. So the sum of the factors of 12 can be rewritten as 2 to the 0 plus 2 to the 1 times 2 to the 2 squared. And this is multiplied by 3 to the 0 plus 3 to the 1, where we go up until the largest prime factor, or the largest degree of the prime factor. So notice how 12 is written as 2 squared times 3 to the first power. And the largest power of 2 we go to is 2 squared, and the largest power of 3 we go to is 3 to the first power. And we can see that when we multiply this out, we get every possible combination. So we have 3 to the 0 times 2 to the 0, and then 2 to the 0 times 3 to the 1, 2 to the 1 times 3 to the 0, 2 to the 1 times 3 to the 1, etc. And these will give us all the factors of 12. So if we calculate this, we get that this is equal to 1 plus 2 plus 4 times 1 plus 3, which is equal to 7 times 4, which is 28. And if we evaluate this by hand, we also get that it's 28. So these are two very useful formulas. They come up fairly often in competition math. So you can look it over more in the handout, and we'll be using this in our later problems for our problem solving. So moving on to our next topic, this is another pretty important topic for competition math. It involves least common multiples and greatest common denominators. Most of you have probably glossed over this topic in school. They don't really teach you much about it. They just tell you what they are. So just as a review, the least common multiple of two numbers, or any amount of numbers actually, is the largest number that is a multiple of all of those numbers. So the LCM of, like, let's say 7 and 12 would be 7 times 12. So that would be 84. But if we take the LCM of, let's say, 6 and 4, it would not just be 6 times 4, because there's a smaller number that's a multiple of both, which is 12, since 4 times 3 is 12 and 6 times 2 is 12. And for greatest common denominator, similar is the greatest common number that divides all of them. So for 6 and 4, it would be 2. And let's say for our earlier example where it was 7 and 12, it would be 1, since only 1 divides both numbers. So how we can find them is that for the LCM, if you look at the prime factorization of the two numbers, so let's look at our second example where we have 6, which is 2 times 3, and 4, which is 2 squared. Basically, for each prime, we take the largest degree. So here we have both of these numbers are divisible by 2, but 4 is 2 squared, whereas 6 only has 2 to the first power. So we take the largest power. So in this case, it would be 4, so 2 squared. And then only 6 has a multiple of 3, so we take 3 to the first power, so that's the largest. And then there are no other prime factors between the two numbers. So this will be our answers. And we can see that 2 squared times 3 equals 12. And if we do this with 7 and 12, we see that we have 7 and then 2 squared times 3. So for 2, obviously only one of them has a power of 2, so it's 2 squared. Then 3, and none of them have 5 as a factor, but then we have 7 again, so we times 7. And this gives us our answer, which is 84. And for the greatest common divisor, we just do like the opposite of this, where instead of taking the largest, we take the smallest. So let's say for 7 and 12, right? We have 7 and 2 squared times 3. We can see that the smallest power of 2 between the two is actually 2 to the 0, because you can write 7 as 2 to the 0 times 3 to the 0 times 5 to the 0 times 7 to the 1, etc. So we can actually take, so that just becomes 1. And then for 3, again, it's also 1 since there's a 3 to 0. And then for 7, although 7 has a factor of 7, 12 does not. So we also take 7 to the 0 again. And this is just equal to 1. And you can see how if we were to do this with our earlier example, 6 and 4, we would take, for a power of 2, both of them are divisible by 2. So we take the smallest power of 2, which is 2 to the 1, and then one of them isn't divisible by 3, so we take 3 to the 0 because that's the smallest power. And this gives us our answer, which is 2. So this is just some basics into LCM and GCD. So there is another common method for finding the greatest common divisor. It's called the Euclidean method. It's much better for very large numbers where it's hard to factor it. So let's say like numbers in the range of like millions or like hundreds of thousands, because factoring those numbers is pretty tedious. This is on our handout if you want to go over it, but it mainly just revolves on like an algorithmic way of evaluating it. So finally, there is a very important property regarding GCD and LCM. So note, we can see that as GCD, since we can take the greatest common divisor and multiply by our least common multiple, so GCD times LCM, and by definition, this should equal the product of the two numbers. And you can see this because when we define our things, you can see how LCM, we were comparing the powers of both numbers and we were taking the smallest number. Whereas for GCD, we're taking the largest number. So basically, if we multiply them together, it should include all the numbers since they come in pairs. They're just ordered in different ways. So you can see for the GCD and LCM of 6 and 4, we have 2 to the second power for LCM and 2 to the first power in GCD. And we can see both of them are in 6 and 4. And the same with 3 to the 1 and 3 to the 0. They're just in a different order. And this is a pretty important property. So now we'll be moving on to our final topic for the day, which is bases and change of bases, arithmetic and bases.
Okay, so in our daily life, we do most things in base 10, which means that we simply group things in groups of 10. Yeah, in daily life, we group things in groups of 10, which means that everything we can also look at things in different bases. In base 3, that would mean that every time you have 3 of a certain object, you move up in place. This will result in the numbers in base 3 being 1, 2, then 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, and so on. So a common question that shows up with bases is how would you convert between bases? Converting from another base to our base 10 is the easier of the two switches, and simply involves considering what does a base mean. So if we had some number, let's say 343 in base 5, that would mean that in this, what used to be the hundredth place is now the 5 squared place. So that would mean that this is equal to 3 times 5 squared, and what used to be the tens place is now the 5's place, plus 4 times 5, and then finally the ones place is still the ones place, plus 3. So this number in base 10 would just be 75 plus 20 plus 3 equals 98 base 10. And the subscript to the left of the number indicates the base. But as we use base 10 in real life, most of the time we don't have to indicate the subscript for base 10, and we can just write the number. So in general, if we have some random number, let's say A, B, C, D, E, in some base x, this would equal A times x to the 4th, since A is the 5th digit, plus B times x cubed, plus C times x squared, plus D times x, plus E. And this can be generalized to as many digits as you want. So going the other way requires a bit more of almost trial and error. We simply have to look for the largest power of B that fits into our number in base 10, and then divide and take the remainder. And you'll keep repeating, and in that way you'll reverse engineer each of these digits. So we can show this through an example. Let's say we want to convert the number 361 from base 10 to base 5. So the first thing to do is find the largest power of 5 that's less than 361, which, as most of you should know, is just 125. As 5 to the 4th would be 625, which is greater than 361. So the 5 cubes place, if we wrote it over here, this would be the 5 cubes, 5 squared, 5, and then units place. So now for the 5 cubes place, we just have to see how many times does 125 fit into 361. And so 361 divided by 125 equals 2 with a remainder of 111. So that would mean our first digit is 2. And again, note that we're using remainders here, and that's a pretty common theme across number theory, as if we're only dealing with integers, we generally don't want fractions or decimals, so the remainder is a lot more important in number theory. In fact, most of our lecture next week will focus on the special properties of remainders, and it's called modular arithmetic, but we'll get more into that later. So now to continue on this problem, now we'll deal with the remainder. The next power of 5 is 5 squared, and it'll fit 4 times into 111 with a remainder of 11, which means that our second digit is 4. Then our next power is 5, which gives us 2 with a remainder of 1. And then finally, 5 to the 0 is just 1, and 1 divided by 1 equals 1, which means that our number in base 5 would be 2421. So in other words, 361 base 10 equals 2421 base 5, as expected. So now we'll move on to some competition problems.
All right, so our first question we have that the digits 1, 2, 5, 7 are each used once, and they're used to form a 4-digit number that is divisible by 4. So the problem asks us to find the largest 4-digit number you can create, which is divisible by 4. So as you can see, the problem obviously relates to divisibility. We want to find numbers that are divisible by 4. So we can use what we know about powers of 4, or multiples of 4. So obviously, if it's a multiple of 4, it's also a multiple of 2, so it has to be even. So this means that 2 has to be the last digit. Now, in order to make a multiple of 4, we need to see that the last 2 digits are divisible by 4. So we just need to check pairs of 2. So that means, since we already know the last digit of 2, the number is 2, which cut down our work by a lot, we only need to check 3 pairs now instead of what was before going to be 6 pairs. So the pairs we need to check are 12, 52, and 72. And if you check all of them, we can see all of them are actually multiples of 4. The first one is 4 times 3. The next one is 13 times 4, or 4 times 13. And then the last one is 18 times 4. So now that we know that all of these work, basically what we need to, since we want to find the largest number, the only restriction we really have is that the last digit is 2. So that means we want to maximize the rest of the number. So that means we want to put the largest number first, because it has like the most weight, because 7,000 will always be greater than 5,000 or 2,000, regardless of what follows afterwards. So using the same logic, the next number will be 5. So because 5 is larger than 1, and then finally we use 1. So our number would be, like many of you guys have figured out, 7,512.
Okay, now for our next problem, we want to find the value of a digit k in this number 4815k6 that will make it divisible by 2, 3, 4, and 9. This is pretty similar to the last problem where we wanted to find a certain number based on divisibility restrictions, but this problem is a lot more since it has to be divisible by 2, 3, 4, and 9. So what we can do from the start is ignore some of the restrictions, specifically 2 and 3. As if it was divisible by 4 and 9, it's automatically divisible by 2 and 3 as well. So therefore, we only need to check 4 and 9. So let's start with dealing with 9. The divisibility rule for 9 is simply that all of the digits sum to a multiple of 9. And the sum of the digits in this number would be 4 plus 8 plus 1 plus 5 plus 6 plus k, which turns into 24 plus k. And as k is a digit, that means for this to be a multiple of 9, k has to equal 3, as k must be less than 9 itself as it's a digit. And now we can just check that it also divides 4. So the condition to divide 4, as in the previous problem, is just the last 2 digits divide 4 as well. And 36 clearly divides 4 as it equals 4 times 9, which means that k equals 3 satisfies both 9 and 4, which means it'll obviously satisfy 2 and 3 as well. Okay, our next problem is of a similar format, but it's slightly more difficult. So it involves a large number with this time two unknown digits. And we want to find the sum of all distinct products of g and h. So to start off, we know that the number is divisible by 72. And while 72 itself, we haven't memorized the divisibility rule for it, we know that the factors of 72 are 8 and 9. So this means we can, instead of testing directly for 72, we can test divisibility for 8 and 9. And if it fits both of them, it'll be divisible by 72 as well. So first, using the divisibility for 9, we find that 5 plus 4 plus 1 plus 5 plus 0 plus 7 plus 2 plus 6 plus our 2 unknowns gives us 30 plus g plus h. And that would mean that the only possible values for g and h are either 6, which would get it to 36, or 15, which would get it to 45. So g plus h equals 6 or 15. So we also know that this, since it's divisible by 8, 2h6 must be divisible by 8 as well. And we can easily test a couple of values for h and find that the only ones that work are 216, 256, and 296. So that would mean that h has to equal 1, 5, or 9. So pairing this alongside our thing where we discovered that g plus h equals 6 or 15, we get that g has to equal 5, 1, or 6. As only one of these is ever possible since g itself is a digit, so it can't be more than 9. So this means that we get 3 pairs, 5, 1, 1, 5, and 9 and 6. Since the first two pairs give the same product of g times h, 5, and the last one gives 54, we have to again carefully read what the problem was asking for to count each possible value only once, which means that our final answer is just 54 plus 5 equals 59. Now we'll go into one more problem about digits. So there are 24 four-digit positive integers that can be formed using each of the digits 2, 3, 7, and 9 exactly once. And how many of these 24 integers are primed? So we can look at this question. This time we want to find primes. And at first it might seem a bit daunting because we don't actually know, we don't have any formal tricks for primes yet. But to be a prime, it simply has to be not divisible by any other number. So to find if a four-digit number is prime would be very difficult, especially with all of the 24 combinations. However, if we look closely, we can check for divisibility by some of the common values, specifically 3. If we add up these four terms, we get 2 plus 3 plus 7 plus 9, which equals 21. And as this is a multiple of 3, that means no combination of these can be a prime, as all of them will be divisible by 3. And this question basically highlights the usefulness of the 3 and 9 divisibility rule. This should always be one of the first rules you check if there's ever asking if a number is divisible or not.
All right, so our next question is if m is a positive integer such that 2m has 28 positive divisors, and yes, the answer to the previous question would be 0. There are no solutions. So if m is a positive integer such that 2m has 28 positive divisors and 3m has 30 positive divisors, then it asks us how many positive divisors does 6m have. So this will be our first question regarding divisors. So if you remember back to when we went back, we had our formula, which said that we had like a formula to find the number of divisors, and that was equal to the part of all the powers plus 1. So we can write m as in the form of, let's say, 2 to the a times 3 to the b, and then times some number k, and we can say k has n factors, hypothetically. So that means m, using our algorithm, would have, since k, or we already know k has n factors, we just need to multiply by a plus 1 and b plus 1. So it would have n times a plus 1 times b plus 1 factors. Now, if we take 2m, we can write it as, instead of 2 to the a times 3 to the b times k, it would be 2 to the a plus 1 times 3 to the b times k. So this would have n times a plus 2 plus b plus 1 factors. And doing the same with 3m, we can write it out as 2 to the a times 3 to the b plus 1 times k. And this would equal n times a plus 1 times b plus 2. And since we know that 2m has 28 factors and 3m has 30 factors, we get two equations. So notice how n divides both of them. So n is a common divisor of the two numbers. And the only common divisors of 28 and 30 are 1 and 2. So we have two cases, one where n is equal to 1 and one where n is equal to 2. So let's first check when n is equal to 1. That means we would have that a plus 2 times b plus 1 equals 28, and a plus 1 times b plus 2 equals 30. And since we know that a and b are integers, we can just test some numbers. So you can see that 28 can be written as 4 times 7, whereas 30 can be written as 5 times 6. So this will give us a solution where a is equal to 5 and b is equal to 3. And we can, and these are the only solutions for where n is equal to 1. Now, if n were equal to 2, we would have a times 2 plus times b plus 1 equals 14, and a plus 1 times b plus 2 is equal to 15. So 14 can be only written as 1 and 14, and then 2 and 7. and 15 can only be written as 1 times 15 and 3 times 5. And we see that none of these pairs work, because we can see that the two factors, a plus 2 divides 14, and a plus 1 divides 15, where b plus 1 divides 14, b plus 2 divides 15. So that means the factor pairs have to only be off by 1, and we see none of these pairs satisfy that. So that means our only solution would be a equals 5 and b equals 3. So that means we have, and we also know that k would equal 1 in this case, or n equals 1 in this case. And since n equals 1, that just means k is equal to 1, because the only number that has one divisor is 1. So that means that m can be written as 2 to the a times 3 to the b, which in this case would just be 2 to the 5th times 3 to the 3rd. Now that would mean 6m would be 2 to the 6th times 3 to the 4th. And using our algorithm again, we can find the number of factors, which would just be 6 plus 1 times 4 plus 1, which is 7 times 5, which is 35. And that's our final answer.
Okay, so our next problem will deal with
All right, so our next question we have, if n is equal to 15 factorial plus 35 factorial, how many of the 9 prime numbers less than 25 are divisors of n? So if you guys don't know what factorials are, you can reference our handout 0. We explained it on there. But I'd assume most of you do. This comes up pretty often. So we'll go on with solving the problem. So we can see that this number n is a very large number. I mean, 35 factorial is huge. So when we want to test whether or not it's factorable, it's pretty daunting. But we can do a lot of things to simplify this. So first, we can note that 35 factorial can be rewritten as 35 times 34 times ... times 17 times 16 times 15 factorial. Which means that since 15 factorial divides both 15 factorial and 35 factorial, that means n is a multiple of 15 factorial. And more specifically, we can write n as 15 factorial times 35 times 34 times 30 times 17 times 16 plus 1. And this is our value of n. So obviously, if n is divisible by 15 factorial, it has to be divisible by 2, 3, 5, and 7, since they're all contained within 15 factorial, and also 11 and 13. However, we also know that 15 factorial does not have any primes greater than 15 in it, since it's less than those primes. So that means if there are any other prime numbers that divide n, they have to divide the other part of our formula for n, which is within this parentheses. But we can also see something special about this number, because if we want to see if it's divisible by the next prime, say 17, we can obviously see that the first part of what's inside parentheses is divisible by 17, since it's a bunch of numbers times 17. But then we add 1. So that means since it's 1 more than a multiple of 17, it obviously can't be divisible by 17. And we can use the same logic for all the numbers from 16 to 35, meaning that no other prime numbers less than 25 can divide that, which means that the only prime factors less than 25 that divide n are the ones that divide 15 factorial, which were 2, 3, 5, 7, 11, and 13. So our answer is 6, yes. So here we have another question involving factors. So the question asks us how many factors of 2010 to the second power, or squared, are less than 2010. So this question will highlight another special property about factors. And this property is that oftentimes factors come in pairs. So going back, remember our example of 12, we had its factors were 1, 2, 3, 4, 6, and 12. Well, we can see that if we split it exactly in half, that they're split exactly into pairs. So 3 and 4 multiplied to 12, 2 and 6 multiplied to 12, and 1 and 12 multiplied to 12. And these are what are called factor pairs. So we can do the same with 2010. So let's start out by finding the number of factors of 2010 squared. So 2010 can be written as 2 to the first power times 3 to the first power times 5 to the first power times 67 to the first power. So 2010 squared would obviously just be this expression squared, which would just be equal to 2 squared times 3 squared times 5 squared times 67 squared. So the number of its factors is just 3 times 3 times 3 times 3, which is equal to 3 to the fourth, which is just 81. So something we come up with a little of an issue because there are an odd number of factors, right? Whereas for 12 we had an even number, so we can split in half. Well, that's because 2010 is a perfect square. So when you split in half, it goes right through 2010. And because 2010 times itself is 2010, we don't count that factor twice. So that means the number of factors less than 2010 is equal to the number of factors greater than 2010, and we also have to include 2010 itself. So if we call the number of factors less than 2010 x, that means we get that 2x plus 1 is equal to 81. So 2x equals 80, which means that x is equal to 40, which some of you guys have already gotten. So that's our final answer, x equal to 40. So this problem highlights, I guess, the importance of factor pairs, and also, I guess, a unique property of perfect squares, that for any perfect square, the number of factors is odd.
All right, so now for our next question. We have Todd who's telling Juanita that he's thinking of a 3-digit positive integer, and the integer has 16 positive factors. The sum of the two of them are 23, and the difference of those is 1. So what is the number that Todd's thinking of? Since the difference of the two factors is 1, we can call the first one x and the second one x plus 1. And so solving the other part of the question, which is that the sum is 23, we get that 2x plus 1 equals 23. Therefore, both 11 and x has to equal 11, and then x plus 1, which is the other factor, would equal 12. So thus the number is a multiple of 11 times 12 equals 132. If we find the prime factorization of 132, we get that it's 2 squared times 3 to the 1 times 11 to the first power. So that would mean, using the formula that we had from the beginning of this lecture, it has 2 plus 1 times 2 times 2 equals 12 factors. So we want to find a multiple of 132, which has 16 factors. So we can either increase the number of factors by either multiplying by 2, 3, or another prime. Respectively, if we multiplied 132 by 2, this would get us 2 cubed times 3 times 11, which would get us 4 times 2 times 2 equals 16 factors, which is what we wanted. But if we had done the other two, let's say if we had multiplied by 3, that would have given us 2 squared times 3 squared times 11 to the first, which would have given us 3 times 3 times 2 equals 18. And the same thing if we had multiplied by 11. Now we could have also multiplied by a completely new prime, but that would have simply added some new power of something new to the first power, which would have increased the number of factors by a factor of 2. And that would have given us 24 factors. Again, not what we wanted. So our final answer is just 2 times 132, which is equal to 264. So this problem basically shows how, like, when you multiply a number, you have to keep in mind what its prime factorization already is when you're looking for the number of factors. As if it's a new factor, it'll simply double the number. But if the factor is already present in the number, it can make the number of factors change in different ways.
All right, so now we'll be moving on to problems involving the LCM and the GCD of number pairs. So our question is, when the least common multiple of two positive integers is divided by their greatest common divisor, the result is 33. And it tells us if one integer is 45, what is the smallest possible value of the other integer? So if you call this other integer, let's say n, right? We know that since the LCM divided by the GCD is 33, that means the least common multiple of the two numbers is divisible by 11. And since 45 is not a multiple of 11, obviously, that means our other number n is a multiple of 11. So we can rewrite this as n equals 11k, let's say. All right, so we have that n is equal to 11k. So since we want to find the smallest number, this essentially just becomes 11 times the greatest common divisor, because n has to be a multiple of the greatest common divisor. Since if it's not, that means the GCD does not divide n, so it's no longer greatest common divisor. And since we want to find the smallest number, it has to be the smallest multiple of both 11 and the GCD, which is just the product of the two. So now that we have n in this form, we can see that n is equal to 11 times GCD, but we also know that since the LCM divided by GCD equals 33, which we're given, then we can rewrite the LCM as 33 times GCD, which is also just 3n. So since we want to find the smallest possible greatest common divisor, and we know that 45 has to divide the least common multiple since it's a multiple of 45. That means we want to find the smallest GCD such that 33 times GCD is a multiple of 45. So 45 has, it can be expressed as 3 squared times 5, whereas 33 only has one multiple of 3. Therefore, GCD has to be a multiple of 15. So the smallest possible GCD would just be GCD equals 15. And we can see that 15 is obviously a divisor of 45. So that means we want to find, that means GCD equals 15 checks out. So that means we can plug that back in to solve for n. So we know that n is equal to 11 times the greatest common denominator, divisor. So that means n equals 11 times 15, which is 165.
Okay, so our next problem is also another example of using the GCD and LCM. In this problem, we're given the GCD of three numbers and pairwise form. 1 second.
All right, so here we have another question relating to GCD. So it's similar to a system of equations where it gives us the greatest common divisor of x and y is 72, the GCD of y and z is 135, and the GCD of x and z is 63. And it wants us to find the smallest possible value of x plus y plus z. So, well, at first it seems a bit confusing because we're not really used to having a system of equations involving greatest common divisor. But what we can do is we can actually use this information in another way. Since we know that 72 is a GCD of x and y, and 135 is a GCD of y, and 135 is a GCD of y and z. That means 72 and 135 both have to be divisors of y. So that means y is some multiple of LCM of 72 and 135. And we can only see this is like in a much better form because we have it as, instead of the GCD of some variable, we have it as the LCM of constants. And we have our variable expressed in terms of that constant. So we can continue this with x. So x is a LCM x is some multiple of LCM of 72 and 63. And then z is the LCM of 135 and 63 times some constant, right? So obviously, if we want to minimize the possible values of x plus y plus z, we want to find the smallest possible values of x, y, and z. So the smallest possible values would be when they are just equal to the LCMs, because if we multiply by some constant, it would increase. Since if you multiply by 2, it would just double. So we take it as y equals the LCM of 72 and 135, x and y, and so on. And we can check. So first, we can evaluate what they would be. So let's start with x in this case. So x would be the LCM of 72 and 63. So if you have paper and pencil, you can do this, but 72 can be written as 2 cubed times 3 squared, and 63 can be written as 7 times 3, or 3 squared times 7. So that means the LCM of those two would just be 2 cubed times 3 squared times 7, which is equal to, if you expand this, it's what is it? It's 504. So doing this with y and z, normally you do this by hand, but we have that y is 1080 and z is 945. All right, so now that I have these, we can check these by hand actually. So we can see the GCD of x and y. So if we write them out as the prime factorizations again, we get that x is equal to 2 cubed times 3 squared times 7, like we already did. Y can be written as 2 cubed times 3 squared times 5 squared. Wait, no, yeah, 5 squared. And wait, not 5 squared, sorry, times 3 cubed times 5. And finally, z can be written as 3 squared, or 3 cubed. 3 cubed times 5 times 7. There we go. Yep. So we can see that the LCM of x and y would be, or the GCD of x and y would be, they both share 2 cubed. The smallest power of 3 would be 3 squared, and the smallest power of 5 and 7 just be 1 and 1 respectively. So it would be 2 cubed times 3 squared, which is 72. So that checks out. The LCM of y and z is, well, z is now a multiple of 2, so it would be 1 for 2. They both share 3 to the cubed, so we would have 3 cubed, and they both share 5, so it'd be 3 cubed times 5, which is 27 times 5, which is 135. And finally, for x and z, we have that the GCD of the two of them would just be 3 squared times 7, which is 9 times 7, which is 63. So all of this checks out. And since we found the minimal possible values, that means our answer would be 1080 plus 504 plus 945. And this number is equal to 2529. And that's our final answer.
All right, so our next problem.
All right, so our next problem, so these problems, we'll be starting our problems on bases. So here it asks us, what is the average of all positive integers that have 3 digits when written in base 5, but 2 digits when written in base 8? And it asks us to answer in base 10. So, well, let's break down our information a bit. So what does it mean when it says it has 3 digits written in base 10? Well, we can write an inequality in base 5. So the smallest 3-digit base 5 number would be 100, or not exactly 100, but 100, written base 5. And this would be equal to 25, since it's 5 squared plus 0 plus 0. And then this is greater than x. or less than x, where x are our possible values, and this and x again is less than the largest possible one, which is 444 base 5, less than or equal to. And 444 in base 5, well, you can think of it as 4 times 25 plus dot dot, but you can also just think of it as 1000 base 5 minus 1, which is just 125 minus 1, which is 124. So this is a useful way in counting. You actually use this in base 10 a lot too, but like it's much more useful in other bases because it's just harder to think in other bases. So we also get another restriction based on base 8. So it has to be 2 digits in base 8. So we can write this as 10 base 8 less than or equal to x less than or equal to 777 base 8 or 77 base 8. And this is equal to just 8 is less than or equal to x, which is less than or equal to 63. So that means that we have 2 bounds. Well, we can see that obviously x is greater than 25 implies x is greater than 8, and x is less than 63 implies x is less than 124. So the restriction really just becomes 25 is less than or equal to x, which is less than or equal to 63. Now, since x can be all the numbers in this range, we want to find the average of all of these numbers. And if you remember back to arithmetic sequences and series, since these are just consecutive numbers, they're an arithmetic sequence. So to take the average, we can just take the sum of the first and last term and average the 2 numbers. So the first and last terms are 63 and 25, so we take the average, so it becomes 63 plus 25 over 2, which is 88 over 2, which becomes 44. And that's our final answer. So moving on, we have a bit more of a difficult problem. So instead of asking us to find numbers in a given base, it wants us to find the base itself, which is a prime p. So it tells us, suppose a prime p, p is a prime such that 1007 base p plus 306 base p plus 113 base p plus 125 base p plus 6 base p equals 142 base p plus 271 base p plus 360 base p. And it asks us how many possible values of p are there. So if you go back to what we did earlier with bases, we know that when we say something is like 1007 in base p, what that really means is that it's equal to p cubed plus 0p squared plus 0p plus 7. And we can do this for all the other numbers. So we then have plus p 3p squared plus 6, then plus p squared plus p plus 3 plus p squared plus 2p plus 5 plus 6 equals p squared plus 4p plus 2 plus 2p squared plus 7p plus 1 plus 3p squared plus 6p. And this is a lot of terms, but if we simplify this down, what this becomes is we get that it becomes the polynomial p to the cubed, or p cubed, minus p squared minus 14p plus 24. Now we'll be using a little bit of polynomials to solve this because solving cubic polynomials is a bit difficult, but we can use a special property of polynomials, which we'll discuss in a later lecture, is that let's say this factors into like p minus a times p minus b times p minus c, right? We can see that the constant term of both of the polynomials, this one would be equal to negative abc, and that has to equal plus 24. So that means all the zeros would have to be a divisor of 24. So we can use what we learned earlier. So divisors of 24 are, since we need to know that we want to find prime bases, right? So we only want to find prime zeros. So that means we want to find the prime factors of 24. So going back, we know that the prime factors of 24 would just be 2 and 3. So that means those are the only 2 possible things that can satisfy this polynomial. But we also notice something else. Since we have the expression 1007 base p, well, that would be impossible in base 2 and base 3 because you can't have 7 in base 2. That would just turn into 1, 1, 1 base 2. And same with base 3. That'll just be like the same thing as writing like 12 in base 10 as 111. It doesn't make sense. So 2 and 3 obviously don't work. Neither of them do. So that means nothing works because those were the only 2 possible solutions and they don't work. So that means there are 0 possible values for P. And that would be our final answer, 0. All right, so we'll be moving on to our last question. So this is a more difficult question. This was from an AMC 12. So the first 2007 positive integers are each written in base 3. How many of these base 3 representations are palindromes? So a palindrome is a number that reads the same backwards as forwards, if you didn't know. So like 121 backwards is also 121. And that would be a palindrome. So we can start out by, since we know that it has to be less than 2007, we can write 2007 as in base 3. So first we want to find the largest power that is less than 2007. So the largest power of 3 that is less than 2007. So do any of you guys know what this would be? All right, as James said, it would be 729. And that would be equivalent to 3 to the 6th power. So not 3 to 6, my bad, 3 to the 8th power. So this is something useful just to know, like knowing like powers of 2 and 3 and 5 and 7 up to a certain extent, because they just pop up a lot and very often. And they can just help you a lot if you see them pop up somewhere. So how many times does 729 fit in 2007? Well, we can multiply by 2 to get 1,458, and that's less than it. And if we add more, it just doesn't work out. So it fits in twice. So if you take 2007 and subtract 729 times 2 from it, we end up with 549 as a remainder. So then the next power of 2 would be 243, and that fits in twice to be 486. So 549 minus 486 is 63. Next power is 81, which doesn't fit in. So then move on to 27, which fits in twice again because 54. So 63 minus 54 is 9. So then 9 fits in once, and then we have nothing left. So everything else would be 0. So this means in base 3, it would be 2, 2, 0, 2, 1, 0, 0. So now we want to find the largest palindrome that's less than this, and that would just be 2202022, which is just 1 less than it. All right, so this probably will be delving into a bit about combinatorics, which will be a lecture in 2 weeks. So we can see something special about palindromes is that if you look at the first 4 digits, each like combination of the 4 digits gives a unique palindrome. So like let's say let's say our first 4 digits are like 2102. That would give the palindrome 2102 and 012. And you can see that the palindromes are ordered in the same way the 4-digit numbers are ordered. So we just need to count all of the palindromes less than or equal to 2202022. So the smallest 7, we can divide this into cases. So you can first consider ones that are 7 digits. The smallest 7-digit palindrome would obviously be 1000001. And the first 4 digits of this are 1000. So then we just want to find all the 7-digit palindromes, which would just be the number of palindromes between 100001 and 2202022. And to do those, we can just count from 1000, the first 4 digits of our first palindrome, to 2202, which were the 4 digits of our next palindrome. Because for each 4-digit number in between these 2 numbers, there's a unique palindrome. So we can find the number of numbers between these 2 numbers, like how we did with arithmetic, with sequence. So we take the upper number, so 2202, subtract 1000, and add 1 again, so that becomes 1210, which in base 3 is 27 plus 18 plus 3, which is equal to 58. So now let's consider 6 digits. So 6 digits, we would only have to consider the first 3 digits. So like it would go up to 22222 and start at 100001. So to count this, it would just be 222 minus 100 plus 1, which is just 200, which is equal to 18. With 5 digits, we can see that again, you only need to consider the first 3 digits, like for 6 digits, because like we had like 121, you would have the palindrome 12121. So then, since it's the same as 6 digits, it's 18. Then with 4 digits, we would only need to consider the first 2 digits. So like let's say the 2 digits were 12, the palindrome would be 1221. So to count this, we would take 22 minus 10 plus 1, which is equal to 20, which in base 3 is equal to 6. And then like before, 3-digit palindromes are the same as 4-digit palindromes. So like 12 would correspond to 121. So this would also just be 6. And then for 2 digits, you would only consider the first digit. So like you would have 11 or 22. So this is obviously 2. And then 1 is the same, you have 1 or 2. So these are all the possible palindromes. So we can sum all these together. So we would have 2 plus 2 plus 6 plus 6 plus 18 plus 18 plus 58. And all of these sum, they sum to 110. And that would be our final answer. So this is definitely a much harder base question, involves some combinatoric counting, but it's very doable, just like with your knowledge of bases and knowing how they work. And you just have to find the right way to count them. So I guess this delves in a lot into combinatorics, and we'll be getting into that in a later lecture. So that's all we have for today. If you have any questions, I know we went a little bit over, so if you have to leave, that's fine. But if you have any questions, feel free to ask. Our homework will be posted in a few minutes. I guess that's it for today. I'll see you, hope to see everyone next week.